Okay, everybody. This actually is the last clip of this video, but I'm going to put it at the very beginning of the video to give you guys a little heads up. Any of you that are watching this, I do not get this thing repaired in this video, and I may not ever get it repaired. I don't know, because we're kind of at a little impasse that I may not be able to get this one fixed, just because of how rare this tuner is, because of how it is designed and put together, how it is built, the availability of parts, very serious lack of any kind of information or anybody that has worked on these before that I can talk to. So this one does not get fixed in this video, and if you do see a follow-up video, it will be because I got it fixed. So and again, this will only be after talking to the owner with this, to kind of see his thoughts, hear his thoughts, what he wants to do. But I apologize in advance. Normally we follow the whole way through on these videos and get them fixed, and you get to see them running in their former glory. This one's not that case. So if you don't want to watch it, I get you, and that's why I'm putting this little clip at the very beginning. Turn it off. It does not get fixed. If you're interested in seeing how these goofy things work and kind of learn along with me, because I learned through this one. Honestly, I had no clue when I first looked at this what they were doing or why or how. It took me a long time to figure some of this out. So again, I apologize in advance. If you still are interested in watching me go through this thing, you're welcome to watch it. If not, I get it. I understand. Take care. Well, hello everybody. We're back. So here's a pretty interesting one. Any of you audiophile tuner nerds out there ought to really appreciate this video. What you see in front of you is a very, very rare piece of equipment. I would definitely classify this tuner as audiophile grade. It's the Pioneer model F-28. I think the only one out there that's more rare than this one is the F-26, which is about half the height of this one and actually even more advanced than this one, has a little bit better performance characteristics. But this one's really kind of crazy the way it's designed. There's very, very little information out there about these. I doubt that you'll see much out there on the internet about it. There's a couple, you might find a little video or picture out there somewhere of somebody turning one on and tuning it around a little bit, but other than that, very rare. It's also reported to be a fantastic performing receiver. Let me read you a little clip that I have from one of the tuner forums out there. The F-28 is a rare quartz synthesized FM-only tuner with 6 gangs. So this has a 6-gang tuner, and before I read any more, there's actually, when you count the actual sections of the tuning capacitor, and yes, this has an analog tuning capacitor in it, you only count 5, but there's actually a 6th tuning gang, and the 6th one is actually a Varicap varactor diode. So it's pretty interesting how they do all this. So it says the 6th digital gang controls the local oscillator, which is used to set the station frequency. This is accomplished by reading the plate. Now, let me show you something in here. Let's see if we can zoom in. And I'm going to kind of move over, and you see, if I put a flashlight in there, looking behind where you're... So here's your little tuning pointer. And if you look in behind there, in behind the dial glass and behind the dial scale, you'll see a bunch of like little black squares, little dots, and they're all the way across there, the dial scale. Those are actually little perforations in a little back plate. And believe it or not, in behind there is a reading element. It's like a photoreactive sensor, and there are actually little lamps inside the tuning indicator itself that shine through those little perforations, and they set up a little digital word. It actually creates a digital word that's picked up on the other side. So it actually knows what part of the dial scale you're on, and then it digitally uses that data to create your actual tuned station. So for instance, not only is it getting roughly tuned with the analog gang, but then it's using a PLL circuit and this little digital sensing setup that they have here, this mechanical digital sensing circuit, to actually create a very precise local oscillator. So even though your intermediate frequency is still 10.7 megahertz like in any other tuner, it actually has a reference oscillator that it uses this digital word with, in conjunction with, to generate a perfect offset, two perfect frequencies, the perfect tuned frequency plus the perfect local oscillator frequency that to create the intermediate frequency. So it's really cool. It's actually that reference signal is somewhere under the 10.7. It's like 10.2 something megahertz. And then it uses this offset to create an exact frequency. So this is a really very, very complicated and very unique circuit design, and unique approach at how you tune. It's kind of analog and digital all in one. So this was kind of the last hurrah, I would say. This one and the F-28 before everything went completely synthesized digital tuning. And that's the appealing thing about this. And what Pioneer was able to accomplish with this one and with the F-28 is nothing short of amazing when you think of how accurate, how sensitive, how selective this tuner actually is, with still having a lot of analog elements to it. The other thing is it has an actual signal strength meter, and if I zoom you on that, you can see it really does. It actually reads out in dBF, and it can read accurately up to 100 dBF at the antenna terminals. This actually is supposed to, as far as I understand, read the actual signal strength and do so accurately. Again, I've never seen one of these in person. I've read about them, but they're so rare you never see them. So actually, someone actually was able to get their hands on one, and they sent it in, and they want me to go over it. I guess this one has some issues. Being the nature of this being so rare and so complex, this is not something we're just going to plug into the wall and turn on. We're going to inspect it inside first. We're going to go over it little by little, and we're going to bring it up very carefully to make sure we don't do any more damage if there is something wrong with this. The other thing, when I received this, it was very dirty and dusty. It had a lot of like pieces of packing foam and things. You can still see some little particles still inside that even got inside the dial area, which is probably blocking up those sensors. So it's going to need cleaned out a little bit, and then we're going to need to go over it and then probably attempt an alignment on it, which actually is pretty involved in and of itself. It goes on for multiple pages, and it is nothing like any kind of alignment that you'll see on a normal tuner. So this should be an interesting video, at least for those of you who are into vintage 70s and so forth audio equipment, because you probably won't get too many chances to see one of these up close and personal like this. So anyways, if that's sounds interesting to you, stay tuned. And who knows, this might end up being a pretty big video. I don't know how involved it's going to get. and I don't know where this is going to take us. Haven't had the covers off, but that's what we're going to start with. We're going to take the covers off, get it cleaned out, inspect it, and then very, very gently start to apply some power to it to see what it does right now before we go any further. All right, stay tuned. All right, here's our first glimpse of the insides. And you can see, just for a plain old tuner, there's a lot going on in here. And the first thing that's already will look abnormal to you is straight down here. And let me move some light around. You can see how many wires are going. This is the tuning indicator. This is the little indicator, and you can see your dial cord. And you can see it plugs down into this board. And you see all these devices here, these little transistor looking things. They're transistors. And right here, it's very hard to see, but this part right here that I'm going across right here, that's the actual digital indicator board. That's kind of like your, it's a piece of acrylic or glass. It's actually glass, and it has the those little holes painted onto it, you know, kind of reverse screen painted. And I don't know if you can see that. You can kind of see some of them down there. If I give you some light, you can see them. And that kind of dial glass paint, at least in my experience, is really, really delicate as it ages. So we're going to have to be extraordinarily careful not to damage any of that while we're in there. We must clean it very carefully and really do not interfere with it any more than is absolutely necessary. Now, if you come over here, our tuning gang is under here, and I've removed the screws, and you can see the tuning gang right there. And there's your 5 right there. 1, 2, 3, 4, 5. And then, of course, the varactor diode, I'm not sure where that is yet. I haven't really looked at the schematics very carefully or anything yet. So just right off the get-go, you can see this is a lot different than any other tuner that we've worked on here, at least on this channel so far. So this should be a really interesting video and a very interesting alignment. So let me get this back together, and I'll flip it over and we'll look at the underneath. So one of the things right away you're going to see, we have the tuner flipped upside down now, and you can see in here they were pretty serious when they designed this power supply. Do you think maybe they were kind of making sure that it was pretty well filtered? I see this integrated circuit here. Again, I haven't looked at the schematic on it yet. But you can see all the voltage regulators, all the just many capacitors that are on here. Obviously, we're going to want to do a recap on this. I don't see any swelling of the caps, and I don't see, at least right from this angle, I don't see anything that looks that it has physically leaked. I'm sure these caps have, some of them have started to go bad. You know, being as old as this thing is, you know, it's over 30 years old, I'm sure. But at least I don't see anything that's, of course, you can't always see if one of these caps is bad. We don't know how long this thing's been since it's really been powered up, you know, knowing nothing about it. But I don't see anything short, you know, that looks bad or burned or anything like that offhand. If we back up a little bit, we can see a little bit more of what the underside of this thing looks like. It's very serviceable, it looks like anyways, in that we can get to the bottom of the boards and the top of the boards without having to remove them. Which, if any of you came along with me for the for the SX939, you can see how involved that can get sometimes. So this should at least not be too bad from a recapping standpoint if the owner decides to do so, which I'm kind of assuming he will. But everything else here looks like, at least right now, we can start to power it up very carefully on a dim bulb and or a variac or a combination of things, and just see at least if this comes up. Again, the little bit of information I did get is that something is not working on this tuner, that there's a problem with it, so we don't know what that is, but I think at least it's safe we can apply some power on it on a limited basis and just see what happens. So that's what we're going to do next. Okay, so we're getting ready to put power to this, and you can see I have a feeling this has been a while since this thing's been used. You can see the green. I don't know if the camera's picking up accurately. It's too much light maybe, but you can see the green tarnish all over this thing. The other thing I like to do is, this is a multi-voltage unit. It can be switched between 240 and 120 volts. And you can see that at 240 volts, you want a half amp fuse or 0.5 amp fuse. And when it's over here on the 120, they want a 1 amp fuse. You can see it is switched for 120. You always want to check that on any of this multi-voltage units, because you don't know, especially if you live over in an area like in Europe where they use 240. If this were switched here like this and you were to plug it in, you'd have problems. Let the smoke out of it real quick. So we check that, and then you want to check your fuse, because the fuse is different depending on what kind of what voltage it's running on. So let's see if we can. And the other thing is, I try to use a plastic screwdriver, unless this is wedged in here real bad, because this Bakelite fuse holders on these, they are notorious for stripping out and cracking. So just one of those things. So let's take this fuse out, and the fuse looks good, and it is can you see that? AGC 1/2 amp. So this actually has the fuse for the 240 volt model in it. Probably been like that forever. I don't know. But that being said, I'm going to leave it in there for right now. But really, this should have a 1 amp fuse. If we go a little bit smaller, the worst that can happen is the fuse could pop. But I have a feeling this is the one that most likely came with the tuner when it was purchased. So there you go. This may have, and it has an American power cord on it, so I have to think it was sold here in the States. It just for whatever reason has that fuse in it, but I'm not going to bother changing it. So we'll clean this all up a little bit here, get some of this dust. I hate getting this dirt all over my hands while I'm working on it. And then we'll put the power to it. Okay, so the record button didn't work on this last frame, so we're going to do a take 2 on it. So I have the receiver set up right now, and we're going to see if we can drive a signal into it. I tried hooking an antenna. It's completely dead. Doesn't even try to tune. So we're going to try to do something. We're going to put a known signal in, and I basically have a wire connected to the antenna jack. It's going over to my signal generator over here, and I have 98 megahertz modulated FM at 400 hertz tone, and I'm putting an uncorrected 100 dBF signal of amplitude. Now, why did I pick 100 dBF? Well, this actually has a signal strength meter that reads in dBF, which is decibels with reference to 1 femtowatt. And as you can see, maximum scale on this meter is 100 dBF. So technically, even though I don't have an impedance matcher in between my signal generator and the receiver, it will be close. It should make the meter go way up when I tune into 98 megahertz. So let's turn it on. Oh, and by the way, coming out of the output jacks, the audio output jacks of the receiver, I just have this little, this is a little amplifier, and it's just simple little thing that we can hear if anything's coming out. So we have this turned on. We're going to turn on the receiver. And it is picking something up, although we're not on 98 megahertz. So I'm going to hold this amplifier close to the mic so you can hear what's going on. There it is again. You can see it's a little more powerful there on 98, which is what you would expect. Here it is again. So it's all over the dial. And as you can see, no matter what, the meter is never even deflecting. So let me turn this back off for now. So what that's telling me is that this receiver doesn't work like the ones that you normally see me work on. It's a lot more complicated. And if you notice, it's never locking in. So it's never seeing, basically I don't think the synthesizer circuit is working properly. Now I'm not sure about that yet, but I think what's happening is that's not working, and because of that the PLL's never locking, so we're never locking into a channel. So you're never, this receiver does not work like a normal receiver that has a standard local oscillator and, you know, a standard RF front end. It's kind of different the way it works. I'd have to get into the theory of operation to explain it, but there's actually a reference signal generator in here, and it uses that reference signal plus this little digital feedback to create your local oscillator frequency. And when you're done, your intermediate frequency is always going to be 10.7 megahertz, but the way it derives it is different than the way your standard receivers will do it. So we need to see if we can find out what's wrong with our synthesizer board first. I just want to see if it's even working, if our local oscillator is working, just see what's going on. So the easiest way to approach something like this, rather than trying to reverse engineer the schematics and the circuit, is to go through the process of trying to do an alignment. Usually when you hit a spot in your alignment procedure that you can't get it to do what it's supposed to do, or it's not reacting the way the instructions are telling you, usually at least that gives you a clue that that's the area that your problem is, or at least somewhere around that area. So that's what we're going to start with before we really get deep into trying to reverse engineer things. We're just going to try to do your basic alignment. And you're going to see this alignment is nothing like the alignments that you've seen me do on other FM stereos out there. This is a very unique design. I think it's very interesting. That's why I'm enjoying this right now, but it is a lot more complicated. So let's start getting set up for that, and I'll be right back. Alrighty, here we go now. So the first thing that we want to do is we're going to, first of all, disconnect this VCO in. Okay, so there's a voltage controlled oscillator, and this part is where your varactor diode is, and it's off on another schematic. And this is partly what's going to set up your local oscillator for your heterodyne. And we're also going to look at our reference oscillator. This is that reference oscillator we're talking about. And it should be somewhere, I believe it's supposed to be not 10.7 megahertz actually. It's actually 10.2323 or 10. Wait a minute, let me look. 10.2325 megahertz. It has to be very, very accurate. So we're going to hook up a frequency counter to this, and we're just going to kind of measure where we are and make sure that at least this little oscillator circuit, and you can see it's a little crystal circuit, this little oscillator here, make sure it is working properly, and make sure that it is properly aligned to that 10.2325 megahertz. Now that's test point 16, so you can see over here we have our VCO in is disconnected, and our test point 16 is right here, and that's probe is going up, and I'm just using this as a ×1. It's just a straight through wire going over to the frequency counter, so we'll look at that here in a minute. So let me get set up here and I'll be right back. Okay, the receiver's powered on and I have the frequency counter set up, and it's a pretty accurate frequency counter, and I have my frequency counters actually plugged in to my GPS disciplined oscillator for my 10 megahertz reference. So this actually is syncing to a GPS DO, so it's going to be very accurate. And as you can see, 10.2329, so it is off a little bit. It should be 10.2325. So to adjust that, we're going to use this really out of focus here. We have to adjust this little trimmer capacitor right here. So I'm going to adjust this right in here, and we're going to try to bring our 10.2325 in line here. So let me zoom you in a little, and let me see if I can get on here, and let's see what we can do. Wow, that is touchy, isn't it? I think that's about as close as I'm going to get it. And of course my kids are stomping upstairs. My whole family stomps. I don't know if you guys have family people that do that, but you know, you kind of get used to it after a while. Hey, that's what you get. You're going to watch my videos. Okay, I think that's as close as we're going to get it. That's pretty good. 10.232503, and it bounces around a little bit. The instructions just say 10.2325, and it doesn't take the decimal out any further than that, so I'm assuming that's pretty much all that. Now it's 23250.1 and it's bouncing. So again, this is not oven controlled crystal or anything like that. Also, probably the age of this thing, the crystal has probably drifted a little bit with age, and they will do that. Any kind of crystal oscillator you run into, you're going to see that, but that's why they make it adjustable on this. So we have that. Now let's go to the next step and see what we have to do next. All right, our next step is we're going to adjust for 122.8 megahertz on TP20. All right, so TP20 is, hold on a second. So to make this a little clearer, or maybe clear as mud, who knows. So we're taking this 10.2325 megahertz, which is right here, and we did see that we were able to adjust that. It then goes through this little circuit right here, and this circuit essentially triples that frequency. So the 10.2325 ends up coming out at about 30.7 megahertz. Then we take that tripled signal and we quadruple it. So really, this oscillator is actually being multiplied by a factor of 12 by the time you're done. So you're tripling it, and then you're quadrupling that, and you're going to come out with 128 or 122.8 megahertz. And then that that 122.8 megahertz signal is what is going to be heterodyned at the front end, and that's going to become that's going to be part of your local oscillator. So and then once you get through all this, that is where the little digital, binary scale inside there is going to come into play. So really what we need to see here is we really should see that 122.8 megahertz right here. And all it is simply is a tripler and then a quadrupler. So let's take a look at that right now. I'm connected up to the test point 20. I have the receiver on, and we know that we have our 10.2325. However, when we look up at our frequency counter, it's all over the place. It's just going crazy. So obviously something on this synthesizer board is not working in that circuit. Now we're not sure what it is yet because we haven't troubleshot it, but it looks like what we're going to have to do is we're going to have to find a point where we can pick up that tripled signal and see if at least we're getting our 30.7 megahertz. So I have to find some place in here, because it's nothing in the book about this. We're going to have to look on the schematics, try to locate a component where we can pick that up and see if we can find at least our 30 megahertz. So that's going to be our next goal. So sorry about all the fan noises. I have the furnace blower in the background, and I have the desoldering station and everything running. But I just want to give you an example of how not to make something service friendly. So this synthesizer module that we have to look at has double shielding on it. So in other words, it has this bottom shield was soldered, as you can see, onto these tabs. These tabs are then soldered also onto the board all the way around, and then protrude through there and make up the top shield. So it's kind of a shield sandwich. Very difficult. You have to very carefully remove all the solder, clean this all off to be able to remove this enough to be able to get into the components in there. I have a feeling that we have a problem in here with one of these components, but I won't know until we get into here and take a look at it. So you just have to be patient. Having a really good solder pump, having a good desoldering station, and some solder wick, and we go through it, and little by little we take it apart. So that's where we are. All right, I have my probe set where I think we should have that 30.7 megahertz, and I'll try to hold this and move the camera. Oh man. And you can see we have 40.9 megahertz, so it is way out to lunch, and I think that's part of our problem. Again, our 10.2 is pretty close. It moves around a little bit, but this is way off. It's not working. So where I'm looking right now, or at least where I think I'm looking, is right here, over here at the junction of these two transistors here. And we should be seeing that 30.7 megahertz right in this area, and we're not. So I'm going to poke around a little bit more and try to figure out what is failing on this board. All right, we have the oscilloscope here, and it's all connected up. And if I go on to my 10.2325 megahertz oscillator, that's what I get. And you can see down there it's saying 10.24. It's bouncing around. And of course the frequency counter on this isn't as good as, you know, the regular frequency counter itself. But you can see these pulses that we're getting. They're not really sine waves, but they're strong. I mean, I'm at 200 millivolts per division, so it's a nice strong signal. If we go over to the tripler, the output of the tripler, which is going to be right here, you can see how far the amplitude has gone down. And it's roughly 40 megahertz, but it's very low amplitude. And we can turn that up if we want, and you can see it's just complete garbage right there. And that's definitely not what I would expect there. Unfortunately, there's no information available, so we have to kind of guess at it, but that's definitely not what I would think a frequency tripler, the output of a tripler, would look like. So we have something wrong in here. It's possibly a bad capacitor. It could be a bad FET. There are some transistors in here. It can be any one of these components can be failing. So yeah, we got our work cut out for us, don't we? Okay, a little update. Rarely do I lose my patience on these things because I find this somewhat relaxing usually. But I must admit, this one is getting the better of me. I believe that the person who invented this tuner was Rube Goldberg. Any of you who know what a Rube Goldberg machine is, I'm sure you'll know what I'm talking about. And if you don't, look it up. That's all I can say. Yeah. So here's where we are. Number one, these two transistors right here are part of the quadrupler circuit that will actually take the 10.2325 megahertz signal. That would be this transistor and this transistor, these two right here. And they're located right here on the schematic. And when we come through this transformer, we're supposed to have about 30.7 megahertz after we triple our 10 megahertz. Then we're going to go through this pair of transistors right here, and we should get a quadrupler here, which will give us 122.8 megahertz right here. Now, this transistor was bad. It took me forever to find it, but it was bad. To make matters worse, you can't just replace the one. You have to have a pair that match. And luckily, I had a really new old stock pair of SK3122s. I did try a different, more common type transistor, and it was no way was it going to work in that circuit. These fortunately worked, and it fixed the problem, at least for here for now. But as soon as you put in this 0.01 microfarad ceramic disc capacitor, which is located right here, having that 0.1, if you notice it's connected, let me get back on here, if you notice it's connected to the base of this Q12, this completely blots out anything over here, and this will not oscillate as long as this is in. Now, I checked this capacitor with two different very high quality capacitor checkers, and it is good. It has nothing to do with that. It's just when you put this in, it snuffs it out. If you take this out, this oscillates. But that isn't the main problem. The main problem is none of this is working properly. And one of the reasons is because you have to have this mess. And this mess comes back to the dial plate. The dial plate has that encoder plate in behind it. And that encoder plate has a bunch of little holes that a light is supposed to shine through into a bunch of photo detectors And those photodetectors then each go to one of these little buffer transistors, which then goes into your PLL circuit to set up your PLL for what channel you're selecting. So you literally have to be over a channel in order to get any of this to work. So if you're not tuned into a station, and that station has to be an equal every 200 kilohertz, if you're not on channel, then it won't tune. That's well and good, but after going through an entire forever mess with this, you come to find out, let me get on here. Okay, here we go. Here's a side view diagram of the dial indicator in the tuner. Here's your dial scale that tells you what station you're on, and then behind it you have the little encoder plate, which I'll show you here in a minute. And then inside this thing is all kinds of stuff, including count them, two little lamps. Those lamps actually are what reflect through the little perforations in the encoder plate and are picked off by the photosensor board, which is right back here, that goes out. It's an 8-bit word that goes into that circuit that we were looking at on the synthesizer board. And then here's your truth table. When you're over top of these frequencies, and yes, you have to align the dial face, the actual frequency dial, with the encoder dial, so that when your pointer is pointing to an actual frequency on this dial, this also has to line up with the correct perforations on this little dial here. So one of these bulbs is burned out. The bottom one is lighting, the top one is not lighting. And the bottom one is actually what gives you this bottom row down here. And that's what, if you notice, let me see if I can find it real quick for you. Because right here, your local oscillator is split up into two sets of frequencies. All frequencies below 99.3 megahertz and all frequencies above and including 99.5 megahertz. So you can see there. So that bottom light takes care of this. The top one is what actually reads the channels, and those channels are what's fed into your PLL chip to tell it what frequency to set the local oscillator and all that to for your phase lock loop. And you can see your 8-bit words going in there. Now, here's the problem. When you look at the dial, here's your dial face. So here's your front face, which actually is the stations. Here's the back plate, which is glass as well, and it has all the little encoder marks on it. And you can see all those encoder marks all the way across there. And if you look down inside here, if I turn the power on, you can see one of the lights come on, but the one on the top is not on. Now, that sounds pretty simple. Just change the bulb, huh? Not so easy. Again, when it's a Rube Goldberg machine, nothing's easy. So this little plastic cover just pulls off. You can see I can pull it part way off. It's just press fit onto these little pins. There's 2 pins on the top and 2 on the bottom. However, in order to pull this off, this dial glass, which is solid glass and very brittle and can break, is in the way. Well, take it out of the way, you might say. Well, you can't, because the side frame here has a metal clip on this side that's spot welded on both sides with this rubber grommet, this little strain relief grommet. And the only way to get this off is to remove this whole side plate right here, which also holds the dial cord pulley. I can't make this up, guys. This is crazy. So I would have to take all this off to be able to take this plastic cover off to be able to get to that bulb and replace it, and still not know if that's going to totally fix it, because in addition to that, and I think that might be related to our problem, but in addition to that, if we go to our schematic once again, and I'll back it up just a little, and you look here, this portion right here, I'm getting this. And if you look at the TP19 that they want you to look at and TP16, those are both good. I have my basic square wave here. It's not really square, it's kind of noisy, but it's there. And you have your 10.2325 megahertz right here that is tunable by this little adjuster, and you have this crystal oscillator. That part works. I'm getting a signal here, but again, with this capacitor in, I get nothing. And even if I remove this capacitor, this part oscillates, this part does not. It doesn't oscillate. Now, there is a possibility that one of these other transistors, either the transistor or the FET or something up in here, is failing and kind of swamping this out. The other thing I noticed is there's a change in this. You can see they upgraded this to a 5.6K. It used to be a 1K resistor. And up here, if you notice, it says changed, and it marks this and circles it as well. This was with the schematic when I got it. And you can see that on this schematic, they're showing this as 4.7K, but they're not showing you what it's changed to. So I'm assuming that is what the value it should be, because they didn't write the value. Now, the couple other places they changed up here, you can see they wrote the value, 100K, 3.3 microfarad, and so forth. But down here, they didn't. And strangely enough, when you look at this, okay, when you look at it, let me get around the camera again so I can find it. Right here, that says 4.7K, but when we go onto the receiver and actually look at it, it's this resistor down here, and if I zoom you in on it close enough, you will notice that it is yellow, purple, orange. That is a 47K resistor, not a 4.7. So, and this is factory. None of this has been touched. This is how I got this receiver. It came like this. So, I don't know if that needs to be a 4.7K. That's a big difference, you know, a factor of 10. So, needless to say, I'm coming to the conclusion that these were not built for a very long time. You know, they only made them for maybe a year or two. I don't know. I'd have to look up the history on it. They're very rare. I doubt that they made very many of them, and now I can see why. It's so over-engineered that, you know, a lot of these things here were not really meant to be very service friendly. If something breaks, it's very difficult to get in there and work on it. And even troubleshooting it can be very, very difficult, as I'm finding out. So I'm inching my way through this, but I look at all this and I'm like, you have to ask the person who owns it, is it really worth it to you for me to put this much time, effort, money, so forth into repairing what's just going to be an FM tuner in the end? I mean, yeah, granted, the specs on a fully functional one of these makes them, this and the F-28, two of the most sensitive high-performance FM stereo receivers ever built. A lot of the forums out there that talk about these things will talk about these things almost like they're a legend, and they probably are a legend when they work. Nobody talks about what happens when they break. And if you go online and try to find information about this, it's almost non-existent. There's no waveforms, there's no not very many threads about people talking about ever servicing them, repairing them. No oscilloscope waveforms or spectrum analyzer frequencies or anything for what it's supposed to look like when it's working properly. So this is becoming very much almost turning into a fool's errand to try to go through and fix this whole thing. I'd love to see it work. It just fascinates me, all that they went through to design this and build it. But at some point in time, you have to ask yourself, when is enough enough? I don't know. So I've got to replace this bulb if I want to get to the next step, which I don't know if that will fix the problem or not, but I've already found one bad transistor, and I was able to replace that. And this bulb, which obviously has to work anyways, even if that's not causing my immediate problem, I will have to replace it or it will not select the channels. That's the other thing. If these bulbs burn out, you have to have a digital word from this encoder plate in order for the tuner to work, because that's an integral part of your oscillator circuit, your IF, your PLL. Everything is kind of tied in. If you read through the theory of operation, everything is kind of tied into this. It revolves around this. Normally on more modern synthesized FM receivers, most of this stuff is done on a couple of chips. This is really being done, I don't know, Rube Goldberg style. So I'm going to probably post this video now as it sits, because just for those of you who are interested in it, and so you can at least see how far I've come and where we are with it. I know this is already a really long video, and I know it's kind of a letdown, so I'm probably going to do a little preview video, little clip to put before all of this to warn you all that I don't get it fixed in this video, so you don't waste your time watching it. But yeah, I'm going to think about this a little bit and then figure out what I want to do from there. I surely don't want to break anything. That's the other thing. I don't want to mess with this glass. I've heard that this paint that they put on here to make these perforations is extraordinarily delicate, and if you put a little chip or a nick in that paint, it will ruin how it tunes. So you really can't mess around taking this out and putting it in. You really don't want to. The dial glass maybe, but again, I don't know if I want to disassemble all this and risk cracking something. I'm going to talk to the owner, but we're going to stop this video right now. And I just apologize. We didn't win this one, at least yet. I definitely lost the battle on this, and I don't know if I'm going to lose the war or not, but we're certainly going to give it a little more thought. But again, thank you all for watching this. And like I said, we'll see what happens next time around. Until then, I wish you all peace, joy, happiness, and good health in your lives. And till the next video, stay well, and we'll see you next time. Bye-bye.